Ancient stones hold secrets modern science is still struggling to explain. We are surrounded by the oldest megastructures on Earth, monuments built with a precision that seems to defy their era. This journey will reveal the sophisticated engineering principles hidden within their colossal frames, showing you exactly how these wonders were built to last for thousands of years. We will uncover how civilizations without advanced tools mastered forces like gravity and earthquakes, and why some of their methods remain superior to our own. What single human quality do you believe was most essential to these impossible achievements? So what exactly makes a pile of stones a megastructure? It is a question of scale, complexity, and purpose. A simple wall does not qualify, nor does a single temple. A megastructure is an undertaking so vast it demands a complete rethinking of what is possible. Think of the Great Pyramid of Giza, a man-made mountain of over 2 million stone blocks, each one precisely placed and aligned to the cardinal directions with an accuracy that still baffles surveyors. Or consider Stonehenge, where colossal stones were transported over immense distances to form a perfect ring that precisely tracks the movements of the sun and moon. These are not just buildings, they are proclamations in stone, projects that would have required the coordinated labor of thousands, a mastery of geometry and logistics, and a vision spanning generations. They were built to last not for decades but for millennia, their purposes often tied to the heavens, to the divine, or to the very identity of a civilization. Understanding this distinction is our first step. It transforms these silent ruins from mysterious piles of rock into the profound engineering puzzles they truly are. And it is within these puzzles that we find the first whispers of a lost science, a set of principles waiting to be decoded. That profound grasp of physics is written in the very shape of the pyramids. Their iconic form is not merely an aesthetic choice, it is a masterclass in structural integrity. The principle of mass and stability dictates that immense weight, when properly distributed, becomes an anchor. The pyramids achieve this through their broad bases and carefully calculated slopes. All that weight from millions of stone blocks is channeled downward and outward, pushing into the earth itself. This creates a structure so grounded, so inherently stable, that it can resist the relentless forces of nature. Think of it as the earliest application of the gravity dam principle, a concept modern engineers would not formally define for thousands of years. The builders understood through experience, not calculation, that a wide, low center of gravity could withstand earthquakes and prevent the ground from shifting beneath it. They were not just piling rocks, they were creating a shape that actively fights collapse. This brute force approach to stability is why these desert sentinels have endured for millennia, a silent testament to an intuitive yet brilliant understanding of how mass can be harnessed to achieve permanence. This celestial connection is etched into the stones themselves. Look beyond the pyramids as mere tombs, and you will find them designed as gateways to the stars. The Great Pyramid's narrow shafts, once thought to be mere air vents, point with uncanny accuracy to the pole star and the belt of Orion. Far across the world, the entire city of Teotihuacan in Mexico was laid out as a mirror of the solar system, with its avenue of the dead and massive pyramids representing the sun, the moon, and even the precise distances between planets. This was not a coincidence, it was a deliberate act of engineering on a breathtaking scale. To achieve this, the builders relied on surprisingly simple tools. A gnomon, which is just a stick planted in the ground, could track the sun's shadow to mark the solstices. Long sighting lines allowed them to pinpoint the rise and set of celestial bodies on the horizon. With these basic instruments, they translated the grand clockwork of the cosmos into perfect terrestrial geometry, achieving alignments so precise they rival what we can do with modern theodolites. This fusion of sky and stone reveals a profound purpose. These megastructures were cosmic clocks, agricultural calendars, and spiritual compasses all in one. They anchored entire civilizations to the rhythms of the universe, dictating when to plant, when to harvest, and when to worship. The sheer precision hints at a forgotten science, a deep understanding of the Earth's own measurements that we are only just beginning to appreciate. But the true test of their genius lies not just in the design, but in the very stones they chose to build with. Across the globe, these ancient engineers demonstrated a profound understanding of material science that seems to defy their time. At Baalbek in Lebanon, they quarried and moved limestone monoliths, each one weighing over 800 tons. That is heavier than a fully loaded jumbo jet. In the Andes, the Inca selected andesite, a volcanic rock of immense hardness, and shaped it into blocks that fit together so perfectly a razor blade cannot slip between them. This was not random selection. It required a deep, intuitive knowledge of geology to locate quarries with the best stone, an ability to read the land and understand material properties like fracture lines and compressive strength. They knew which rocks could bear immense weight and which would shatter under pressure. Their quarrying techniques were equally brilliant. To free a massive block, they would often heat the stone surface with fire and then rapidly cool it by dousing it with water. The thermal shock would create a network of fine cracks, allowing them to split the rock with astonishing precision along its natural grain. In other cases, they drilled rows of holes and hammered in wooden wedges. When the wedges were soaked with water, they would expand with immense force, cleanly shearing the stone along a predetermined line. Then came the Herculean task of transport, moving these multi-ton behemoths across miles of rugged terrain, often without the wheel. This speaks to a masterful command of logistics and simple physics, using lever systems, lubricated earthen ramps, and sheer human coordination. The stones themselves are a lasting testament to a deep, practical partnership with the Earth, a knowledge that turned the bones of the planet into timeless monuments. Moving beyond brute mass, these builders unlocked a deeper secret, the intelligent management of force itself. They learned to guide weight, to persuade it to travel along paths of their own design. This mastery of load distribution is what separates simple heaviness from true structural genius. You can see it in the corbelled arch, a technique perfected by both the Mycenaeans in Greece and the Maya in Central America. Instead of a single keystone, these arches are built by stacking stones in ever closer rings, each layer cantilevering slightly inward over the empty space below. The weight of each new stone is not just dropped downward, it is cleverly redirected. The force travels diagonally, channeled along the angled faces of the stones, and sent outward into the thick, robust walls on either side of the opening. This transforms a vulnerable gap into a moment of incredible strength, a doorway that supports immense loads from above by elegantly shunting that energy to the sides. It was an early, brilliant solution to one of architecture's greatest challenges, how to span a space without letting it collapse. But perhaps the most breathtaking application of this principle comes from the Inca. Look at their walls, those mesmerizing puzzles of polygonal stone. Every block is a unique, irregular shape, with multiple interlocking facets and angles. They fit together so tightly that the entire wall behaves as a single, unified mass. When an earthquake strikes, a wall of rectangular blocks will shake as one rigid unit. The straight lines and right angles become points of weakness, and the structure can easily crack and crumble, but an Inca wall is designed to dance. The complex, jigsaw-like joints allow the stones to shift and slide minutely against each other during a tremor. The seismic energy is not concentrated, it is dissipated. The force is dynamically redistributed across the entire network of stones, moving through the wall like a wave that loses its power as it spreads. This is not just building for today's stillness, it is engineering for tomorrow's chaos. These methods reveal an empirical, hands-on understanding of physics that we would later codify with mathematics. They knew how forces travel, and they built structures that could not just bear weight but could think on their feet. These simplest machines were the engines of the ancient world. The lever and the inclined plane, two basic concepts, became the most powerful tools for moving the immovable. While they lacked complex machinery, these builders possessed a deep, intuitive grasp of mechanical advantage. This is the principle that a small force, applied over a longer distance, can overcome a large resistance. A lever is a perfect example. By sliding a strong timber beneath a stone and placing a pivot point or fulcrum close to that stone, a team of workers could amplify their collective strength. With a coordinated push on the long end of the lever, they could pivot a multi-ton block upward, just enough to slide rollers or a new foundation underneath. This was not brute force, it was calculated force. It allowed for the delicate, inch-by-inch positioning of stones that needed to fit together with perfect precision. But lifting a stone is one thing, raising it to the soaring height of a pyramid is another. For that, they turned the very landscape into a machine. The evidence at Giza points to the use of massive ramps, which are just inclined planes. These were not simple dirt piles. They were monumental engineering projects in their own right, built with compacted earth, timber reinforcements, and their own retaining walls to prevent collapse under constant, heavy traffic. Some theories suggest straight ramps rising steeply from the quarries, while others propose magnificent spiraling ramps that wrapped around the growing pyramid structure. Imagine teams of laborers not just dragging blocks, but walking them up these gentle slopes. The ramp transforms the impossible vertical lift into a manageable, gradual incline. The distance traveled is vastly increased, but the effort required at any single moment is dramatically reduced. This was mechanical advantage executed on a breathtaking, almost unimaginable scale. It was through the combined power of the lever and the ramp that these mountains of stone were assembled, one deliberate, calculated step at a time. Yet the greatest structures were often built to harness an element far more fluid than stone. Water was the true lifeblood of ancient empires, and the engineering required to command it rivals the most magnificent temples. Across the arid landscapes of Persia, a hidden network of tunnels called qanats snaked for miles beneath the desert sands. These were not simple ditches, they were subterranean aqueducts, masterpieces of hydraulic engineering that tapped into water trapped deep within mountain aquifers. The genius was in the gradient. To bring water to the surface without pumps, the builders had to carve these tunnels with a perfectly consistent, gentle slope from the mountain source all the way to the city or farmland. A slope too steep would make the water rush and erode the tunnel walls. A slope too shallow would stop the flow entirely. Achieving this required surveying over vast, unseen distances with astonishing accuracy, using little more than sighting poles and water levels. It was a monumental, invisible achievement that turned deserts into gardens and sustained cities for centuries. On the other side of the world, the Khmer Empire built Angkor Wat, a city of 1 million people in the Cambodian jungle. Its true marvel was not just the temple, but the vast hydraulic machine surrounding it. A complex network of massive reservoirs, canals, and moats acted as a giant water management system. During the monsoon, these structures captured and stored immense volumes of rainwater, preventing catastrophic floods. In the dry season, the same system released water through intricate sluice gates to irrigate vast rice paddies, enabling multiple harvests each year. This was civil engineering on a staggering scale, demonstrating a profound understanding of hydrology, soil mechanics, and seasonal cycles. These ancient engineers were not just moving water, they were taming it. They understood its power, its necessity, and its dangers, and they built megastructures to negotiate a permanent peace with this most vital resource. But these builders were not just managing forces, they were encoding a deeper truth into the very bones of their structures. A third principle governed their work, one of geometric perfection and proportional harmony. Look at the Parthenon standing atop the Acropolis in Athens. To the eye, it is simply beautiful, but its beauty is rooted in a precise mathematical secret, the golden ratio. This ratio, often represented by the Greek letter phi, is approximately 1.618 to 1. It is a proportion found throughout nature, in the spiral of a nautilus shell and the arrangement of seeds in a sunflower, and it is universally perceived as harmonious. The Parthenon's entire facade, the relationship between its width and height, the spacing of its columns, all adhere meticulously to this divine proportion. It was a deliberate choice, an application of a mathematical principle believed to connect human creation to a universal cosmic order. This pursuit of sacred geometry extends to the Great Pyramid. The ratio of its base perimeter to its height is remarkably close to 2 pi. This suggests its builders might have encoded a fundamental understanding of this constant, the very relationship between a circle's circumference and its diameter, into the pyramid's immense physical form. Achieving such precision on a monumental scale was a staggering feat. It required not just advanced surveying, using tools like gnomons and sighting lines with unbelievable accuracy, but also a standardized unit of measurement that could be consistently applied by thousands of workers over decades. A single cubit's variation could have thrown the entire divine proportion into chaos. This was engineering as a high art. The goal was not merely a stable building, but a structure that resonated, that felt right because it was mathematically right. They were building a bridge between the earthly and the celestial, using stone and geometry to mirror the perfect harmony they believed governed the universe itself. Beyond the silent geometry of stone lies a hidden dimension of these structures, the dimension of sound. A fourth principle emerges, one of acoustic engineering and sonic resonance, demonstrating that these builders were masters not only of physical forces but of the very air itself. In the subterranean depths of Malta's hypogeum, a labyrinthine underground temple carved from solid limestone, there is a chamber known as the Oracle Room. Speak a word in this small, oval space, and your voice does not just travel, it transforms. The sound is amplified, carried with unnatural clarity to every corner, while certain lower frequencies seem to be swallowed by the stone. This was not an accident. It was the result of the chamber's meticulously carved shape, its concave walls acting like a parabolic dish to focus and project sound waves. The builders even selected the specific type of limestone for its resonant properties, understanding that the very material of the walls could shape the experience of a whisper into a divine proclamation. Far across the Atlantic at Chichen Itza, another acoustic marvel awaits. If you stand at the base of the massive El Castillo pyramid and clap your hands, the sound does not return as a simple echo. It comes back as the distinct, warbling chirp of the sacred Quetzal bird, a creature deeply woven into Mayan cosmology. This effect is created by the sound waves traveling up the steep staircase. The tread of each step acts like the teeth of a comb, filtering the sound and breaking the single clap into a rapid series of reflections that our ears interpret as a bird's call. This intentional manipulation of sound reveals a profound sensitivity. These spaces were not just for viewing, they were for listening and for being heard. The engineering was in service of ceremony, using physics to create awe, to make the human voice carry the weight of the gods, or to summon the spirit of a sacred animal from the very stones. It shows us that their genius extended to the intangible, designing environments where sound itself became a sacred technology. The stones themselves could never have risen without the human spirit to lift them. These monuments are as much a testament to social engineering as they are to physical engineering. To build a pyramid or a great wall required a society that could function like a single, colossal machine. Imagine the sheer scale of coordination, feeding thousands of workers, providing shelter, and managing a complex supply chain that stretched for miles, all without a single computer or telephone. This was not a chaotic mob of laborers. It was a meticulously organized workforce, a hierarchy of skill and responsibility. At the top were the master architects and skilled stonemasons, the engineers of their day. Beneath them were legions of quarrymen, haulers, and carpenters, each group performing a specialized task in a carefully sequenced operation. This level of organization required a sophisticated administrative system, one capable of planning years in advance, tracking resources, and maintaining morale. How do you motivate a person to spend their life moving stones for a project they will never see finished? It was not merely the crack of a whip. Evidence from worker villages near the Giza plateau reveals they were well fed with bread and beer, received medical care, and were buried with honor. This suggests a system of rewards and a shared ideology, a belief that they were part of something divine, something that would immortalize their entire civilization. The megastructure itself became the ultimate tool for state building. It unified a scattered population under a common, monumental goal, transforming tribes and villages into a nation. The real wonder is not that they moved multi-ton blocks, but that they moved an entire society to achieve the impossible. This ancient principle of management, of inspiring collective action toward a shared vision, is a form of engineering that remains just as powerful today. Sometimes the most profound lessons are found not in success, but in a spectacular failure. Deep within the granite quarries of Aswan in Egypt lies the unfinished obelisk, a colossal shaft of stone that fractured and was abandoned where it lay. This single cracked monument is an open-air classroom, a frozen moment of ancient engineering that reveals more than 1,000 finished structures ever could. It is a textbook written in stone. You can still see the precise, ruler-straight channels that workers painstakingly carved around the obelisk's intended shape, isolating it from the living bedrock. In the trenches they hammered out, you can almost feel the presence of the teams who would have driven in rows of wooden wedges. Their technique was a masterpiece of applied physics. They would have soaked those dry wedges with water, and as the wood swelled, it generated immense, irresistible pressure, a force that traveled through the stone along its natural grain, cleaving it from the earth with surgical precision. This was not brute force, it was controlled fracture, yet here the stone fought back. A hidden flaw, an unexpected stress point, caused a catastrophic crack to spiderweb through the monolith. In that single, heartbreaking fracture, we see the immense risk and staggering ambition of this work. Moving a completed obelisk of this size, likely intended to stand over 100 feet tall and weigh more than 1,000 tons, would have been a logistical miracle. Seeing this project halted in its tracks makes the flawless obelisks that now stand in Luxor and Rome seem all the more miraculous. This abandoned giant does not mark a defeat, it immortalizes the process, showing us the raw, physical truth of how these impossible stones were born. High in the Andes, the fortress of Sacsayhuaman challenges everything we assume about ancient construction. Its walls do not rise in straight, orderly lines. Instead, they form a series of dramatic, jagged teeth against the sky, built from limestone blocks so colossal that their transportation remains a mystery to this day. But the true wonder is not the size of these stones, it is how they fit together. Each block is a unique, irregular polygon, with multiple angles and facets that lock perfectly with its neighbors. The joints are so impossibly tight that you cannot slip a piece of paper, let alone a razor blade, between them. This was not just meticulous craftsmanship, it was a revolutionary approach to building in a land constantly shaken by the earth itself. The Inca looked at a world of tremors and understood a fundamental truth. A rigid wall built with uniform rectangular blocks will resist a quake as a single, brittle unit. The straight lines and right angles become lines of stress, points of failure where the entire structure can crack and crumble. But Sacsayhuaman's polygonal masonry is designed to be flexible. When an earthquake strikes, the energy does not meet a solid, unyielding wall. It meets a dynamic, interlocking puzzle. The stones, with their complex shapes and beveled edges, can shift and rotate minutely against one another. They absorb the seismic shock, distributing the force across the entire network and allowing the wall to literally dance without breaking. The grinding process used to achieve this fit was a testament to relentless patience. Imagine workers repeatedly lowering a multi-ton block onto the one below, using abrasive sand and water to slowly, methodically grind the surfaces until they mirrored each other with inhuman precision. This was not a quick process, but the result was a structure that behaves as a single, unified mass, one that has withstood centuries of violent tremors while modern buildings around it have fallen. The Inca chose a path of immense effort to achieve a timeless goal, proving that sometimes the strongest shape is not a perfect rectangle, but a perfectly fitted puzzle. That same principle of resilience finds its ultimate expression in a material that feels almost magical. While the Romans were not the first to build with stone, they perfected a recipe that gave their structures a supernatural longevity. Their secret was not in the stone itself, but in the mortar that bound it together. Roman concrete was a revolution in material science, a pinnacle of ancient chemistry that we have struggled to match. Its most famous showcase is the Pantheon in Rome, a temple crowned by a massive, unsupported dome that has stood for nearly 2,000 years. The dome is a single, breathtaking shell of concrete, and its secret lies in a special ingredient mixed into the mortar. The Romans discovered that by incorporating volcanic ash known as pozzolana, they could trigger a remarkable chemical reaction. When this ash combined with lime and seawater, it formed a crystalline structure that was not only incredibly strong but could also cure and harden even when completely submerged. This is why they could build harbors that resisted the relentless erosion of the sea, their concrete actually growing stronger in the saltwater. Think of modern Portland cement, the kind we use today. It is prone to cracking over decades, especially when exposed to water and the elements, yet Roman concrete, with its volcanic heart, seems to defy time. It possesses a self-healing quality where tiny cracks are often filled in by continuing chemical reactions within the material itself. This was not an accident. It was the result of deep, empirical observation. The Romans saw the way certain volcanic soils hardened when wet, and they experimented, they refined, and they created a perfect, localized solution. They understood that by manipulating the properties of the materials they found around them, they could engineer a substance that would outlast their empire. The most astonishing part of this story is that the precise recipe was lost for centuries after Rome's fall. We are only now, with advanced microscopes, beginning to unlock the full molecular secrets of their concrete, secrets that its builders understood through sheer, brilliant practice. This relentless innovation through failure is a story told in the very landscape of Egypt. The smooth, perfect pyramid we envision was not a sudden invention. It was a goal achieved through a century of experimentation, a dramatic evolution carved in stone. Look at the Pyramid of Djoser at Saqqara, the first colossal stone structure ever built. It began as a simple mastaba, a flat-roofed tomb, but its architect Imhotep had a grander vision. He stacked mastaba upon mastaba, each level smaller than the last, creating the step pyramid. It was a revolutionary leap, but also a first attempt. The builders were learning how to handle massive stone weight, how to prevent the structure from collapsing inward under its own mass. The next great experiment came with the pyramid at Meidum. It started as a step pyramid, but a later pharaoh ordered its steps to be filled in, creating the first attempt at a smooth, angled side. This project may have ended in a partial collapse, a catastrophic lesson in the critical importance of a stable foundation and the correct slope. Then came the bent pyramid at Dosha. Its lower section rises at a steep, ambitious angle, but partway up, the architects clearly saw the structure beginning to show stress. Cracks may have appeared. Instead of pressing on toward disaster, they made a crucial mid-construction correction. They changed the angle to a shallower, more stable slope for the upper portion, creating its distinctive bent shape. This was not a design flaw, it was a brilliant, on-the-fly adaptation. It was the direct, empirical application of a lesson learned the hard way. Every crack, every settling foundation, taught them more about the behavior of stone and earth under immense pressure. They were discovering the principles of the angle of repose, the steepest slope at which a material remains stable, not through equations but through observation. This cumulative knowledge, paid for in failed projects and corrected mistakes, culminated in the flawless geometry of the Great Pyramids at Giza. Their perfection is not a sign of infallible genius from the start, but the magnificent final product of generations of builders who were not afraid to learn from what went wrong. Yet these monumental projects, spanning longer than a single human life, demanded more than just skill. They required a perfect continuity of knowledge. How do you ensure the grand vision for a pyramid begun by a pharaoh is executed flawlessly by his grandson's generation, all without a single written blueprint? The answer was a living chain of wisdom, a master-apprentice system that transferred understanding as much as technique. A young person would enter the service of a master builder, not for a few years but for decades. They learned by doing, by feeling the stone, by listening to the sound a hammer made on a specific grain, by developing an intuitive sense for the perfect angle. This was knowledge passed from hand to hand and from ear to ear, embedded not in documents but in ritual, story, and even song. The precise ratio for a pyramid slope might be encoded in a chant. The correct method for setting a foundation stone might be part of a ceremonial practice. This made the knowledge a sacred cultural inheritance, something too vital to be lost. To maintain absolute consistency across generations, they relied on standardized units of measurement. The Egyptian royal cubit, a length of about 20.5 inches, was not just a ruler. It was a physical artifact, often carved from black granite and kept under the guard of a priestly caste or the master architect himself. All measurements across the entire kingdom, from the quarry to the rising apex of the pyramid, were derived from this single, sacred standard. This system of hands-on training and rigid standardization created an unbroken thread of expertise. It allowed a project begun by a master to be continued by his students, and then by their students, with no deviation from the original divine plan. The very existence of these finished megastructures, built over a century with perfect consistency, is the ultimate proof that this living library of human experience worked. The most astonishing part of this story is not the scale of their ambition, but the profound simplicity of their tools. Scattered around the quarries and foundations of these megastructures, archaeologists have unearthed the real evidence: copper chisels worn down to stubs, stone hammers cracked from repeated impact, fragments of heavy wooden sledges, and coils of rope. These were the instruments that built the impossible. We have tried to replicate their methods, a field known as experimental archaeology. Teams of researchers, using only these reconstructed tools and ancient techniques, have shown us how it was done. A copper chisel might seem soft against granite, but when paired with a stone hammer and a steady, patient hand, it can pulverize the rock grain by grain. A massive stone block can be moved by a large team on a lubricated wooden sledge, proving that with enough coordinated human effort, even a 1,000-ton obelisk can walk. The principles they used were not alien, they were the fundamental laws of physics made tangible. Leverage, friction, and the power of a simple inclined plane became their most advanced technology. This is why the theories of lost civilizations or extraterrestrial architects are not just fanciful, they are a disservice to human history. To credit some outside force is to rob our ancestors of their genius, their perseverance, and their hard-won intellect. The true wonder is not that someone from the stars came to help, but that human beings with nothing but stone, copper, and incredible determination achieved works that still leave us breathless. The real mystery we should be solving is how they saw so much potential in such simple things, and in that answer, we find a far more inspiring story about our own species. There was no line drawn between what a structure was meant to be and what it was meant to do. This is the core of their genius, a seamless fusion of form and function where every single element pulled double duty. Think of the Great Pyramid's smooth, angled sides. They reach for the sun's rays in a powerful symbolic gesture, but that very same slope is the key to its physical immortality, a shape perfected through trial and error to distribute colossal weight and resist collapse. Or look at the Parthenon, where those fluted columns rise in perfect proportion. Their grandeur is meant to inspire awe, yet their swelling form, slightly thicker in the middle, is a direct response to the immense stone entablature they carry. The aesthetics are not an afterthought, they are a physical expression of the forces at work. This principle extends to the smallest details. High on the ramparts of a Gothic cathedral, a grotesque gargoyle stares down from the rain gutter. It is a fearsome piece of sculpture, a guardian against evil spirits, but its open mouth is a meticulously carved spout, designed to throw rainwater away from the fragile masonry walls below. The art is the engineering. This reveals a fundamental truth about these builders. The roles of architect and engineer were not separate professions. They were a single, unified vision. A person designed a structure not just to stand up, but to speak, to embody a culture's beliefs, its understanding of the cosmos, and its relationship with the natural world. Beauty was not applied like a coat of paint. It emerged naturally from solving a problem in the most elegant and efficient way possible. This holistic philosophy stands in stark contrast to our modern world, where design is so often compartmentalized, where an engineer ensures a building stands and an architect makes it look pleasing, two separate conversations that sometimes struggle to find a common language. These ancient stones remind us that the most enduring creations are born when purpose and poetry are the very same thing. These structures felt less like intrusions and more like natural extensions of the earth itself. Ancient builders were master adapters, engineering with the landscape, not just on top of it. They understood that the most resilient design is one that listens to its surroundings. High in the cliffs of Mesa Verde, entire cities were tucked into massive natural alcoves. This was not just for defense. The overhanging rock provided a brilliant, passive form of climate control, shielding the dwellings from the scorching summer sun while allowing the lower winter sun to warm the stone walls. The alcoves also protected the delicate masonry from relentless wind and driving rain, using the mountain itself as a permanent, indestructible roof. On the other side of the world, in the flat, sun-baked plains of Mesopotamia, builders faced a different challenge. They lacked abundant stone, but they had earth in endless supply. Their genius was in transforming this humble material into a perfect building block. They mixed mud with straw and packed it into molds, leaving the bricks to bake hard in the desert sun. These sun-dried mud bricks were more than just convenient, they were perfectly adapted. Their porous nature allowed them to absorb heat during the day and release it slowly at night, creating a natural temperature regulation system inside the homes. Even their grandest structures, the towering ziggurats, were engineered for this specific climate. They were not solid piles of brick. Builders constructed them with a ventilated core, a network of gaps and channels that allowed air to circulate deep within the structure. This prevented moisture from being trapped and weakening the bricks, a simple yet profound solution to a potentially catastrophic problem. Every decision was a response. They oriented buildings to capture cooling breezes or block dusty winds, to maximize the low winter sunlight or create deep pools of summer shade. Their work was a continuous, intelligent dialogue with the forces of nature. This principle of sustainable, context-sensitive design is a lesson modern engineering, with its reliance on universal materials and energy-intensive climate control, is only now fully rediscovering. These ancient builders knew a fundamental truth we sometimes forget, that the most elegant engineering does not conquer the environment, it collaborates with it. That colossal pile of stones is a testament to a pyramid of grain. The physical weight of the monument is dwarfed by the economic weight of the system that built it. Before a single block was quarried, an entire civilization had to pivot toward this singular goal, and that required a surplus. You cannot ask thousands of people to stop farming and start hauling stone unless you have already figured out how to feed them. This demanded an agricultural revolution, a society so productive with its land that it could generate a massive, reliable food surplus year after year. Think of the Nile Valley, its fields enriched by annual floods, producing more barley and emmer wheat than the local population needed. This surplus was the true fuel for the pyramids. But how do you collect and distribute that fuel? A complex system of taxation and tribute, managed by a growing class of scribes and administrators, acted as the civilization's circulatory system. Grain was gathered from farms across the kingdom, stored in vast state granaries, and then distributed as daily rations to the workers' villages. We know from ancient records that laborers received a steady allotment of bread and beer, the staples of life. This was not slavery in the brutal sense, but a form of state-organized labor paid in the most essential currency of all, food. The logistical network stretched far beyond the bakery. Sourcing the finest white limestone from quarries across the river, or the granite for sarcophagi from Aswan, hundreds of miles to the south, was a supply chain miracle. It required the seasonal flooding of the Nile to be harnessed. During the inundation, when the fields were underwater and farming halted, the river became a liquid highway. Heavy blocks were loaded onto massive barges, their journey timed perfectly to the high water, floating the immense weight with an efficiency that land transport could never match. Where the river did not reach, temporary roads of packed earth and timber had to be constructed, roads strong enough to support sledges carrying stones heavier than a modern tank. This entire operation, from the farmer's field to the mason's chisel, was directed by a centralized authority with unprecedented power. Only a pharaoh, seen as a god-king, could command the resources and labor of an entire nation for a project that spanned generations. The pyramid's perfect geometry is the final expression of a much larger, invisible structure, a pyramid of power, logistics, and economic management that truly mobilized a civilization. This unity of purpose is the final, master principle behind every stone. The ancient world did not separate the spiritual from the structural. A pyramid was not first a stable shape that later gained a symbolic meaning. Its meaning as the primordial mound of creation, or as the descending rays of the sun god Ra, is what demanded its form. The engineers were then tasked with making that sacred vision a physical reality, and in doing so, they discovered that the most potent symbol was also one of the most stable structures in existence. The same is true for the great stone circles. Their circular form was not an arbitrary choice for a gathering place. It embodied a core belief in the eternal cycles of the sun, the moon, and the seasons. The circle has no beginning and no end, a perfect representation of the cosmos. But this symbolic requirement also created a defined, acoustically resonant space and a permanent astronomical observatory. The engineers, bound by this sacred geometry, had to solve the immense practical challenges of transporting, shaping, and erecting multi-ton stones into a perfect ring. The meaning dictated the impossible task, and the engineering genius found a way to accomplish it. This fusion is why these projects were pursued with such breathtaking ambition over generations. It was not a simple public works program. The drive came from a profound belief that by building these structures, the civilization was participating in the cosmic order, reinforcing the harmony between heaven and earth. The stability of the pyramid was not just about physics, it was about the stability of the universe itself. The perfect alignment of a stone circle was not just about tracking stars, it was about ensuring the sun would rise again. When spiritual belief and physical law converge in a single, unified vision, it creates a motivation powerful enough to move mountains or to build them from scratch. That ancient genius is not locked in the past, it is alive in the steel and concrete that surrounds us today. The principles they discovered through trial and observation form the very bedrock of our modern world. Look at the graceful arc of a Roman aqueduct, and you will see the direct ancestor of every soaring bridge arch and every vaulted ceiling in our grandest train stations. That simple, powerful shape which channels weight downward into sturdy piers is a concept that has never been improved upon, only refined with new materials. The Egyptian mastery of mass and stability is the same principle that allows a modern gravity dam to hold back an entire reservoir. These colossal structures rely on their own immense weight, channeled through a broad base, to resist the monumental pressure of the water, a direct echo of the pyramid's fight against the desert sands. Even the Inca's brilliant seismic wisdom is finding new life. In an age of skyscrapers, engineers are designing buildings with base isolators, systems that allow the entire structure to sway independently of the shaking ground, a high-tech translation of those interlocking stones that learn to dance. The lever and the inclined plane are everywhere, from the hydraulic jack that lifts a car to the winding on-ramp of a multi-story parking garage. These are not just echoes, they are a continuous lineage of problem solving. By studying these ancient laboratories where experiments have been running for thousands of years, modern engineers gain something priceless, a profound appreciation for first principles. Sometimes the most elegant solution is not a complex new invention, but a timeless idea waiting to be remembered. The past offers a catalogue of proven strategies, challenging us to look beyond our digital screens and remember the fundamental physics that these master builders knew by heart. These divergent paths in engineering philosophy tell a story of two different conversations with the world. Look at the Parthenon in Greece or the Colosseum in Rome. Their language is one of geometry and conquest. Straight lines, perfect circles, and right angles assert a human order upon the landscape. They relied on the post and lintel, a system of vertical columns supporting horizontal beams, a testament to their mastery of compressive strength. The goal was to create a defined, idealized space that stood apart from the wilderness, a monument to human reason and power. Now travel east. The Great Wall of China does not fight the mountains. It flows over them like a stone river, its path dictated by the peaks and valleys. It is a work of terracing and earthworks, a structure that embraces the land's natural contours for both strategic defense and structural stability. In Mesoamerica, the pyramids at Teotihuacan were not isolated sculptures. They were carefully integrated into the sacred landscape, with the nearby mountain, Cerro Gordo, forming a central part of the city's celestial axis. This was not a battle against nature, but a collaboration. The available materials reinforced this split. The Mediterranean world had abundant marble and limestone, perfect for carving into precise blocks. The East often worked with what was underfoot, rammed earth, brick, and adobe, materials that demanded a more fluid, adaptive approach to form. This fundamental difference is a cultural fingerprint. Was the universe a system of perfect forms to be replicated, or a living entity to be harmonized with the stone's answer for them? A Roman aqueduct marches in a relentless straight line, a declaration of human will. The Great Wall dances with the dragon spine of the mountains, a testament to a philosophy of integration. Engineering, it turns out, is never just about what you build, but why you build it and the world you are building from. For all our brilliant deductions, the past still holds its cards close. The silent stones of Newgrange in Ireland guard one such secret. Its massive entrance is sealed by a single, immense capstone, a rock weighing many tons perched high atop the structure. We understand the ramp that likely brought the stones for the walls, but how did they lift this final, crucial piece to such a precise height and angle without leaving a single scratch or clue to their method? The mystery only deepens when we travel to the jungles of Costa Rica and find the perfect stone spheres. Hundreds of these orbs, some taller than a person, were carved from hard granite with a symmetry so flawless they appear manufactured by a machine. Their purpose is utterly lost to time. Were they astronomical markers, symbols of power, or components of a vast, forgotten geomantic map? We simply do not know. Then there is Puma Punku in Bolivia, a site that defies belief. Its stone blocks are not just large, they are intricately carved with geometric precision, featuring razor-sharp corners, perfect right angles, and complex interlocking channels that look as if they were cut with a diamond-tipped saw. The andesite stone they used is notoriously hard, yet the workmanship is so exact it suggests a level of tool technology we never knew existed in the ancient Andes. These are not just puzzles, they are open challenges. They drive a new wave of research where archaeologists are no longer just using shovels and brushes. They now deploy LiDAR, a laser scanning technology that can see through dense forest canopies to reveal the ghostly outlines of entire cities hidden for centuries. Ground-penetrating radar sends pulses deep into the earth, mapping buried chambers and foundations without moving a single stone. Each scan, each new digital map is a promise of a revelation. The story of ancient engineering is not a finished manuscript gathering dust on a shelf. It is a living, breathing field of inquiry, an active construction site of the mind where every new discovery has the power to topple a long-held theory and force us to see our ancestors in a startling new light. Every stone was laid not just to withstand time, but to command the human spirit. These megastructures were engineered to produce a specific, overwhelming feeling, a visceral awe that reinforced the social order from the moment you laid eyes on them. The Great Pyramid did not simply stand, it loomed, a man-made mountain designed to make any individual feel microscopic and insignificant. This deliberate dwarfing of the person was a direct expression of the pharaoh's divine power, a psychological anchor holding society in place. The experience was carefully scripted. Imagine the journey of a priest or a high official moving from the bright, open desert into the pyramid's shadow. They would enter through a narrow, cramped passageway, forced to stoop or crawl, their world reduced to a dark, confining tunnel. This was a physical and mental constriction, a stripping away of one's sense of self. After this long, arduous ascent in near total darkness, they would finally emerge into the king's chamber. Suddenly, the confinement vanished, replaced by a soaring, granite-walled vault, a hidden universe of perfect geometry and profound silence. The shift was jarring, transformative. It was a choreographed revelation, moving from humility to grandeur, engineered to instill a state of reverence and shock. The builders were masters of this emotional architecture. They understood that the manipulation of space, light, and scale was as crucial as the manipulation of weight and force. They designed pathways that built anticipation, chambers that inspired terror or transcendence, and facades that made authority feel absolute and eternal. This was engineering with a dual purpose, shaping both stone and the human heart, making the structure itself an instrument of power and belief. From the lever to seismic resilience, these hidden principles form a legacy of human ingenuity that is both humbling and profoundly inspiring. Our journey has taken us through the mastery of mass in the pyramids, the celestial precision encoded in stone circles, the revolutionary chemistry of Roman concrete, and the invisible architecture of social organization that mobilized entire civilizations. These monuments do not stand as silent relics of a mysterious, lost world. They are something far more powerful, enduring proof of what humanity can accomplish with careful observation, relentless collaboration, and sheer determination. Their stones speak a universal language of problem-solving. They tell us that genius is not always about having the most advanced technology, but about seeing the deepest potential in the world around you, in a simple lever, a pile of mud, or the slope of a hill. The greatest engineering feats are born from this deep, intuitive understanding of our world and our place within its systems. So the next time you see an image of these ancient wonders, we hope you see them with new eyes, not as puzzles, but as testaments. We would love to hear which principle you find most astonishing. Was it the cosmic alignments, the earthquake-proof puzzles, or the sheer will that moved mountains? Share your thoughts and keep the conversation with our past alive.